All right, everybody, here is the part 2 video for homework 1, consisting mostly of simplifying radicals. So let's do some examples. For this first section, we have that we don't want any perfect squares left inside square roots or any perfect cubes left inside cube roots, and that extends to any idea. So we don't want any perfect fourth powers left inside fourth roots, and so on and so on and so on. So what that typically means is we have to be able to factor the number inside the root, which we call the argument. So 75 is the argument of the square root function here. Sorry, I'm a little lovely. So we could factor this kind of however we see fit. You might recognize it's 3 times 25. Oh, that looks terrible. But if you didn't, you might say, well, I know 5 is a factor, and 75 divided by 5 is 15. So it's 5 times 15. And you might write that as the square root of 5 times 5 times 3. The square root of 5 times 5 is 5. So it comes out, and you can write this as 5 root 3. And that's our simplified as much as possible answer because we've pulled out all the perfect squares from inside the square root. Alternatively, if you had seen this as just 25 times 3, you could have said to yourself, oh, the square root of 25 is 3. So this becomes, in fact, I'll write an additional step. You don't need to write this step, but you could say the additional step here, which gives us still the answer of 5 root 3, is saying the square root of 25 times 3 is the same as the square root of 25 times the square root of 3. And then the square root of 25 is just 5. But really, the easier kind of more efficient way of doing it is to look for pairs in the square root and say, oh, the square root of something times the same something is just that something. We're going to do the same idea here. So 80, again, I'm going to start factoring. So I'm going to see a square factor of 4. I'm going to think of 80 as 4 times 20. And then I could even write that as 2 root 20. But then 20 can be factored further. 20 is equal to 4 times 5. Gosh, I'm really sorry. And the square root of 4 is 2 again. So I really have 2 times 2 times the square root of 5, which is 4 root 5. There are lots of different ways to have done this. You might have recognized from the very beginning that, although probably not, I didn't see it from the very beginning, that 80 is 16 times 5. So the square root of 80 is the square root of 16 times 5. And then the square root of 16 is 4. And the square root of 5 is left behind. Either way, we get 4 root 5 as our result. Or some people say 4 rad 5. I usually say root if I'm talking about a square root. For any other root, I will say the cube root. So like 4 cube root 5 or whatever, if it's a different root other than the square root. Cube root of 80. So now we're going to pull out any perfect cubes. So we might recognize that 80 again is, well, I didn't actually, not again, but instead of doing 4 times 20, I might see it as 8 times 10, because that's kind of easy. And then the cube root of 8 is 2. So we get 2 cube root 10. But maybe you don't see that right off the bat and you just start factoring. So if I was going to take a longer path, gosh, sorry. I might just start dividing by 2. Good God, that's terrible. So we get the cube root of 2 times 40, which is equal to the cube root of 2 times 2 times 20, which is equal to the cube root of 2 times 2 times 2 times 10. If you really wanted to factor it all the way, you could say it's the cube root of 2 times 2 times 2 times 2 times 5. And then these 3 2's, since it's the cube root of 2 times 2 times 2 is just 2. So it's 2 times the cube root of, I'm left with 2 times 5, which is 10. So either way you want to see it's fine. Just depends on what's more comfortable for you. If you recognize that 8 is a factor of 80 and you know that 8 is a perfect cube, it might be easier to do this way. If you don't, it might be easier to do this way. Same idea, 4th root of 80. So now, since we've already done the work before, let's go ahead and just write this as the 4th root of 2 times 2 times 2 times 2 times 5. But the 4th root of 2 times 2 times 2 times 2, or 2 to the 4th, is just 2. So it's 2 times the 4th root of 5. So basically, whatever your root is, you need that many of them to kind of pull it out in front of the root. So the fourth root of 2 times 2 times 2 times 2 is 2. The cube root of 2 times 2 times 2 is 2. The square root of 2 times 2 is 2. That idea holds. So just as an extra example here, I know that the fifth root of the following thing, right? 2 times 2 times 2 times 2 times 2 times 3, which is 96, right? That's 4, 8, 16, 32 times 3 is 96. So the fifth root of 96, well, since I have 1, 2, 3, 4, 5 twos, the fifth root of 2 times 2 times 2 times 2 times 2 is just 2. And then you're still left with the fifth root of 3. So the fifth root of 96, I didn't start with that, but that's how you can write it, is equal or simplified as 2 times the fifth root of 3. You just need that many twos to pull out one of them. I should point out, because some people get confused with this, the 5 twos in the fifth root come out as 1 2, not in the fifth root. So just kind of like a little frog in my throat. It's really terrible. So let's look at the last one here. Last one in this part. Square root of 108, I'm going to do the same thing. I'm going to start just dividing by, or really factoring convenient things. So square root of 108, I can see is 2 times 54. And then I like just starting with 2's. 54 is 2 times 27. And then 27 is 3 times 9. Now I could pull out these 2's in front, right? I could write this as 2 root 27 or 2 times 2 times 27 inside. I kind of like just leaving it. So I see 3 times 9. And if you really want to go all the way, it's 2 times 2 times 3 times 3 times 3. So the square root of 2 times 2 is 2. The square root of 3 times 3 is 3. And you're left with a 3 inside the radical. So we would finally simplify this as 6 root 3. Again, just to show you an alternate path, you could have, although it's harder to see right off the bat, that 108 is equal to 30, God, 36 times 3, and the square root of 36 is 6. So again, there's lots of pathways to simplify a square root, but the end result should always be the same, no matter which path you take. So the question kind of comes up then, why bother simplifying radicals at all? Well, one reason is so that we can add or subtract them. For example, the square root of 108 plus the square root of 75 plus the square root of 28. We're going to simplify each of these as much as possible and then see if we can add some of them together. So we just saw from before that the square root of 108 is 6 root 3. So let's not repeat the work we've already done. The square root of 75, I feel like we did that one in the beginning as well, but let's write that again. 75 is 25 times 3. So that's going to simplify as 5 root 3. And then 28, I can see that 28 is 4 times 7. And 4 is a perfect square. So rewriting this, we have 6 root 3. That is a 3. Sometimes my 3's look a little messy. I'm sorry about that. Plus 5 root 3 plus 2 root 7. Because again, the square root of 25 is 5. The square root of 4 is 2. We can add the 6 root 3 and the 5 root 3 because essentially you have 6 of this thing plus 5 of this thing. And 6 of something plus 5 of something is 11 of it. It's like you had 6 apples and 5 apples. You have 11 apples. If you have 6 root 3's plus 5 root 3's, you have 11 root 3's. And then the 2 root 7 just stays as is. And that's it. I really should specify here, you cannot add square roots together by just adding their arguments together. So I should point out that this is not equal to the square root of 108 plus 75 plus 28. Probably the most well-known example of this, which I will write. No, I should do it right now, which I'm going to write to the side here. Let me grab another piece of paper. Just kind of give you another example of how we know that's not true. My favorite example of how you can't do this is the square root of 9 plus the square root of 16 does not equal the square root of 9 plus 16. Let's check. Square root of 9 is 3. The square root of 16 is 4. And 9 plus 16 is 25, and the square root of 25 is 5. And oh yeah, 3 plus 4, which is 7, definitely does not equal 5. So we really, really, really cannot add square roots together by adding the arguments together and then taking the square root of the whole thing. Okay. One more simplification here. So we're going to add these cube roots together in the same way. We're going to simplify them as much as possible, and then we're going to add any terms together that have the same radical left. So both of these had a radical 3. We add them together. Here, we're going to see something similar. So here we have to find groups of 3 things multiplied together. So the cube root of 24 is the cube root of, let's just factor as much as possible. 24 is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. You can also write the little chart thing here, right? If it helps, you can do like 24 is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. That's a totally, totally fine way of doing that. 81 is similar. You might recognize the 81. It's kind of hard. I know that 81 is divisible by 3 because 8 plus 1 is 9 and 9 is a multiple of 3. That's a trick for seeing if something's divisible by 3, is if the numbers add up to a multiple of 3. But 81 divided by 3 is kind of a pain. I would rather do the 81 is 9 times 9, and then 9 times 9 is 3. Or sorry, 9 is 3 times 3, 9 is 3 times 3. So 81 is really fully factored 3 times 3 times 3 times 3. The cube root of these 3 2's multiplied together is going to be 2. The cube root of these 3 3's multiplied together is going to be 3. So what I end up getting is 2 cube root 3 plus 3 cube root 3. All right, so those 3 2's inside the cube root become this 1 2 outside the cube root. Those 3 3's inside the cube root becomes this 1 3 outside the cube root. And then I have 2 of a thing plus 3 of the same thing, right? Those are both 2 cube root 3 and 3 cube root 3. So 2 plus 3 is 5 cube root 3. Not too terrible. Okay. We can also multiply radicals together. The nice thing about multiplying radicals together is you actually don't have to simplify them first. So there's a couple ways to go about this. And actually, let me kind of talk about the harder way first. So 4 times root 12 plus 5 times root 12. The 4 times 5 we can multiply together and get 20. And the root 12 times root 15, I'll point out you have the square root of 12 times the square root of 15 is the same as 12 to the 1/2 power times 15 to the 1/2 power. And when you have two different numbers, oops, sorry, you can't see that. Apologies, I make that mistake occasionally, sorry. When you have two different numbers multiplied together raised to the same power, you can just multiply those numbers together. So this really you could think of as 12 times 15 to the 1/2 power, which is the same as the square root of 12 times 15. 12 times 15, well, the way I do multiplying by 15 is 10 times 12 is 120. 5 times 12 is half of that, which is 60. And 120 plus 60 is 180. And the problem is now we're going to have to factor this out to make it simpler. So we really could have saved ourselves some time by not multiplying the 12 by 15. So I would rather write this as 20 times the square root of 12 times 15. And we'll finish this and I'll address one more thing. So then I really just want to write 12 to the 15 factors as much as possible. So 12 is 3 times 2 times 2. 15 is 3 times 5. Oh, look, I have a pair of 2's and a pair of 3's. So I'm going to be getting 20 times 2 times 3 times the square root of, there's still a 5 left behind in there. 20 times 2 is 40. 40 times 3, well, 4 times 3 is 12, so 40 times 3 is 120. So I have 120 root 5. Do you want to address one thing I said up here? When you have two different numbers raised to the same power multiplied together, you can just multiply the insides together and keep the power the same. Another example of that would be if you had something like 2 squared times 3 squared. You can either just say it's 4 times 9, which is 36, or you can say it's 2 times 3 squared, which is 6 squared, which is 36. So either way is correct, but it's just I wanted to point out that you really can, when you're multiplying two things together with different bases but the same power, you can multiply the bases together and then take the power of that. Okay, another example of multiplying radicals. Again, you do have to have the same root because you have to have the same power, right? The cube root of 18 times the cube root of 20 is really the same as just 18 to the 1/3 times 20 to the 1/3. So let's write this as 4 times 7 times the cube root of 18 times 20. And again, gosh, sorry. I'm sorry for all the noise I'm making on this video. It's not lovely, I know. For 18 times 20, I don't want to multiply it out. It is 360, but that's not really helpful. It's better to factor things. And I'm going to try and factor so that well, I was almost say 18 is 2 times 9, but the 9 isn't helpful because it's not a square root. I want a cube root, and the cube root of 9 is not a nice thing. So I'm going to say the 28 times the cube root of 18 is 9 times 2, which is 3 times 3 times 2. And 20 is 4 times 5, which is 2 times 2 times 5. And look, I have a 3 of a kind. So that 2 can come out. And I'll have 28 times 2 times the cube root of 3 times 3 times 5. I should simplify this. 28 times 2 is 56. And times the cube root of 3 times 3 is 9. 9 times 5 is 45. So this is kind of gross, but this is as simple as that expression gets. All right, let's look at this next one. I would say stop me if you have questions, but it's not that kind of video. So if you have questions, really though, you should stop the video or pause the video and try and work on a problem yourself, or look at some examples from the homework, or look at some examples from Grant's website, or send me a message. Square root of 6 plus square root of 24, quantity squared. So we're going to have to square or FOIL this out. This is equal to the square root of 6 plus the square root of 24 times the square root of 6 plus the square root of 24. And the reason we say the word FOIL, which I didn't know until I got to college, is because it stands for first, outer, inner, last. But really, this means you kind of multiply each thing in here by each thing in here. So we're going to do the root 6 times the root 6. That's the first. The root 6 times the root 24. That's the outer. The root 24 times root 6, which is the inner, times. And finally, the root 24 times root 24, which is the last. Now, a couple things to recognize here. This is kind of a typical pattern. When you have something plus something quantity squared, you always get the first thing squared, right? This is the square root of 6 squared. You get the two things multiplied together twice. So you get 2 times the first thing times the second thing. So I have one of those there and one of those there. The order of multiplication doesn't matter. And finally, you get the last thing squared. So the square root of 6 times the square root of 6, we should get comfortable with saying that's just 6. So we can take another step if you want to. You can say it's the square root of 6 times 6, or 36. But really, we should skip that step and just say it's 6. Here, we're going to simplify this as 2 times the square root of 6 times the square root of 24. I want you to see that this term and this term are the same. The order of multiplication does not matter. 3 times 5 is the same as 5 times 3. And same deal over here. This last part is the square root of 24 times the square root of 24, or the square root of 24 times 24. And although we could break this down into lots of different factors, you know that we have a square root of something times something, right? We have a pair here. The square root of a pair multiplied together is going to end up being just that number. So the square root of 24 times the square root of 24 is just going to be 24. So here's what we've got. We've got a 6 here. We're going to simplify this in a second. We've got a 24 here. Let's actually multiply this out. So we'll multiply that, meaning like we're going to simplify the square root. So we've got 2 times the square root of, as a reminder, the square root of 6 times the square root of 24 is the square root of 6 times 24. 6 is going to be 2 times 3. 24 is going to be 8 times 3, which is 2 times 2 times 2 times 3. Did I pick a perfect square? I think I might have. So I'll point out that if you actually multiplied 6 by 24, you would get 144, and you might recognize that the square root of 144 is 12. We can also see that here. We have a pair of threes, we have a pair of twos, and we have another pair of twos. So that ends up being 6 plus 2 times 2 times 3 times 2, right? We have two pairs of twos and one pair of threes, which 2 times 3 times 2 is 6 times 2 is 12. So yeah, the square root of 144 is 12 plus 24. And that's going to equal 6 plus 2 times 12 is 24, plus another 24 is going to be 30 plus 24, which is 54. Now I'll point out, not all these examples are going to come out to be a perfect, nice integer. Most of the time, you'll have another square left over. I'm going to, interesting. I didn't write numbers on these, which is atypical. I meant to. This should have been number 8. Sorry about that. This should have been number 9. And this should have been number 10. Where are we at time-wise? We're kind of long time-wise here. We've only got, yeah. So, yeah. Let me throw one more example at you there, just because I do feel like it's worthwhile to point out that you don't always get something so nice. So let's say we had square root of 5 plus the square root of 7 squared. That's going to be the same thing. It's going to be square root of 5 times square root of 5. Actually, let me write it out the long way. Root 5 plus root 7 times root 5 plus root 7. Right? Squaring is just repeated multiplication. And that's going to be root 5 times root 5, which is 5. Root 5 times root 7, which is going to be the square root of 35. Root 7 times root 5, which is also the square root of 35. And root 7 times root 7, which is 7, or the square root of 49. And then we have 5 plus 7, which is 12. And square root of 35 plus square root of 35 is 2 times the square root of 35. See how this one simplifies and isn't a nice integer like the previous example. That's what I want to point out. Is most of the time problems like this, you won't get a nice, just single integer value. All right, rationalizing denominators. So why would you rationalize the denominator, first of all? Well, I should say, what is rationalizing? Rationalizing the denominator means we're removing the radicals from the denominator. And a reason why you might do this is it's actually easier to approximate a thing. For example, if you know that the square root of 2 is about 1.414, then we could say that 1 over root 2 is approximately 1 over 1.414. But that's not like super helpful. It doesn't really tell me what's going on. So then I'd actually have to like do the division and say, okay, well, 1 divided by 1.414. And I have to like move the decimal over 3 places. Then I have to do 1414 into 1,000. And then I'm like, I don't know, like, is it 7 times maybe? 7. I don't want to do this. 7 times, right? 7 times 4. It's just a pain, right? And I'm doing it the wrong way. It should be 8 and then 9 and then, yeah, 8. Right, that seems, I feel like I'm off by a decimal place, right? It should be like 1 over. Terrible. Instead, we should do the following. We should rationalize this. So we're going to multiply this by the square root of 2 over the square root of 2. Because any square root multiplied by itself is just the number inside. This is going to be 1 times root 2 on top over the square root of 2 times 2 on the bottom. Really, you would skip this step and say, oh, the square root of 2 times 2 is the square root of 4, which is 2. And then that's our final answer. Oh, it's not our final answer. I said the square root of 2 times 2 is the square root of 4. Sorry, not the final answer. And then that's equal to the square root of 2 divided by 2. That's our final answer. Apologies. And now the nice thing about writing it this way is it's much, much easier to do the division if we're trying to approximate it. If you're trying to do this equal to approximately 1.414 divided by 2, it is much, much easier to divide by a single digit divisor. And right, so 2 goes into 14 7 times. 7 times 2 is 14. Perfect. Bring down the 1. 2 goes into 1 0 times. 0 times 2 is 0. Bring down the 4. Or sorry. Yeah, 0 and then subtract. and then bring down the 4. 2 goes into 14 7 times. So it's much, much easier to calculate that square root of 2 divided by 2 is approximately 0.707, as opposed to trying to do this terrible division over here. So that's one reason why we like to rationalize the denominator. Another is it's just considered to be the simplified form. Looking at this one here, we're going to multiply by whatever your radical is in the denominator. So we're going to multiply by root 12 over root 12. I should say this is true for square roots. If you had a different kind of root in the denominator, the process is a little bit more challenging, which we're not going to get into. So that's going to be 8 root 12 divided by the square root of 12 times the square root of 12 is just 12. And again, right, you can write that if you want to. Square root of 12 times the square root of 12 is the square root of 12 times 12, which is 12. Or you can say it's the square root of 144, which is 12. You don't really need to show that work. It's always accepted that the square root of the number times the square root of the same number is just that number. And then we can simplify this. We can divide a 4 from the top and the bottom and say that's going to be equal to 2 root 12 over 3. 8 divided by 4 is 2. 12 divided by 4 is 3. If you want to see the extra steps there, we could have written that as 4 times 2 times root 12 over 4 times 3 times, sorry, just 4 times 3. And then 4 divided by 4 is 1. So you're left with 2 root 12 over 3. Now, when your denominator is a radical plus or minus some other number, which could or could not be a radical, then we have to multiply by what's called the conjugate. So the conjugate of a something plus something else, something minus something else is the same exact thing, except the addition or subtraction is switched. So the conjugate of root 7 plus 2 is root 7 minus 2. And we have to multiply by the same thing on the top and the bottom because you can't change the expression. We're just multiplying by 1. It's just a weird looking 1. It's root 7 minus 2 over root 7 minus 2. The top is easy. You're just going to get 6 times root 7 minus 2. And we're going to distribute that 6 in the next step. So it's a little kind of cluttered here. Apologies. On the bottom, same idea. You're going to get root 7 times root 7. Right, we're foiling this out. So root 7 times root 7 is just 7. You're going to get root 7 times negative 2, so minus 2 root 7. You're going to get 2 times root 7, so 2 root 7. And you do, like when I said 7 times negative 2, sorry, root 7 times negative 2, you do want to write the integer part in front of the radical part. That's why I wrote this negative 2 root 7. And then finally, 2 times negative 2 is minus 4. Notice that the negative 2 root 7 plus the positive 2 root 7 is going to add up to 0. So we end up getting 6 times root 7 minus 2. And actually, I'm not going to distribute the 6 in just yet because I have 6 times root 7 minus 2 divided by 7 minus 4, which is 3. And then 6 divided by 3 is 2. So you should wait to distribute that until you maybe have done any division that's possible here. 6 divided by 3 is 2. So I get 2 times root 7 minus 2. Or if we FOIL it out, sorry, distribute it, it's not really foiling. You get 2 root 7 minus 2 times 2 is 4. Same idea here. In fact, you should try this one on your own before you watch me do it. Pause the video, multiply the top and bottom by the conjugate, and then see if you get the same answer that I get. All right. I'm going to multiply by the square root of 8 plus the square root of 3 over the square root of 8 plus the square root of 3. The things that are, so the bottoms are conjugates. Root 8 minus root 3 is the conjugate of root 8 plus 3 and vice versa. The tops are not. So for the whatever things are not conjugates, you're just going to write it as 10 times that thing. Whichever things are conjugates, you want to multiply it out. And fun fact, whenever you multiply conjugates together, like for example, a minus b times a plus b, there's always a pattern. And the pattern always is a times a is a squared. The middle terms always add up to 0. You get a times b minus b times a, which adds up to 0. And then finally, minus b times b is minus b squared. So you always end up getting the first thing squared minus the second thing squared. That always happens when you multiply conjugates together. So we could show all the work here, or we could say, hey, I know that root 8 minus root 3 times root 8 plus root 3 is going to be the square root of 8 squared minus the square root of 3 squared. So that's going to end up being 10 times the square root of 8 plus the square root of 3 all over 8 minus 3. 8 minus 3 is 5. So you get 10 times root 8 plus root 3, all divided by 5. 10 divided by 5 is 2. So you get 2 times the square root of 8 plus the square root of 3. Or if you distribute it, 2 root 8 plus 2 root 3. Either way is probably, just like here, either of these answers is considered simplified. Same is true here. Either of these answers is totally acceptable. But this is an important thing to know, that whenever you multiply conjugates together, the middle terms always end up adding to 0, and you just get the first thing squared minus the second thing squared, just like we did here, right? Root 7 squared is 7, and minus 2 squared is 4. Cool. All right, last page here. Radicals are just exponents. The square root of 13 is the same as 13 to the 1/2 power. The cube root of 18 is the same as 18 to the 1/3 power. And any radical, like say the fifth root of 73, is the same as 73 to the 1/5 power. Which means if we're trying to simplify a thing, it often makes sense to write everything as powers instead of radicals. For example, if I want to simplify the cube root of 5 to the 6th, I'm going to write it as 5 to the 1/3 to the 6th. And then when you have a power to a power, we can multiply those powers. So I can really write this as 5 to the 1/3 times 6. 1/3 times 6 is the same as 6 divided by 3, which is 2. 5 squared is 25. Just to clarify on this here, 1/3 times 6 is the same as 1/3 times 6 over 1. And when you multiply fractions together, you multiply across. So you get 1 times 6 over 3 times 1. And then 6 divided by 3 is 2. Here, we have 25 to the 1/6 times 25 to the 1/3. When we have bases multiplied, when we have bases with powers multiplied together, we add the powers, right? That's our additive law of exponents. So it's going to be the same as 25 to the 1/6 plus 1/3. To add those fractions, we need a common denominator. 1/6 plus 1/3 is the same as 1/6 plus 1/3 times 2 over 2, which is 1/6 plus 2/6, which is 3/6, which reduces to 1/2. So we end up getting, I should have maybe given myself a little bit more room. We end up getting that this is equal to 25 to the 1/2, which is the square root of 25, which is 5. Cool. I will admit, I did pick examples that turn out nicely here, just because I kind of wanted to see some. Same idea as the first one here. The cube root of the square root of 64 is the square root of 64 to the 1/3 power, which is really 64 to the 1/2 to the 1/3. Power to a power, you multiply the power, so that's 64 to the 1/2 times 1/3. 1/2 times 1/3, 1 times 1 is 1, 2 times 3 is 6. So it's 64 to the 1/6. So 64 to the 1/6, well, you could think of that as the 6th root of 64. I didn't mean to write that so big, sorry. But then 64 is exactly 2 times 2 times 2 times 2 times 2 times 2. It's 6 2s. So the 6th root of 64 is exactly 2. You might have been able to see that more easily if you hadn't done all this work, although I really wanted to show the work of writing a radical as a power to a power and then simplifying it that way by multiplying the powers. But I will also point out that we could have done this by seeing that we have the cube root of the square root of 64. You might know that the square root of 64 is 8, and the cube root of 8 is 2. All right, that's all there is to this video. Sorry, it was a bit long. I will try to keep them shorter in the future.